Thanks, Brittany, for inviting me, and thanks to the committee for thinking of making inviting me to share all these these abstracts that I did in the past 3 years. It's been a fun experience to go back into those 3 years and make a summary of all of this and notice how I did a lot of work and this work is leading into something that I think is very interesting, and I'm very happy to share it with you today. So today I'm going to talk about uncovering the brain vasculature in vivo. But before going deeply into that, I wanted to go back a little bit in time and talk about some preliminary work that I did during my PhD that led towards this overarching goal of understanding the brain vasculature. So during my PhD, at first, my project was to try to find biomarkers of Alzheimer's in MRI, and it was based on PET-FDG images. So basically, wanted to look at fMRI and see if there was some concordance with PET-FDG glucose metabolism. And by doing regional analysis, we found that the regions that had a high glucose metabolism had also some high fMRI signal amplitude or local homogeneity. Sorry. So basically, there was a concordance at 80% of accuracy of prediction from fMRI to say if there's a high glucose metabolism in a region. So for us, it raised a few questions because those are two very different modalities, and we didn't think that this was that possible. And so we wondered if there was some common physiological characteristic that we could maybe find in those two different acquisitions. And for us, the main hypothesis was the vasculature. So basically, we needed to develop some tools to accurately model the vasculature and then look at those vascular density in different regions and maybe try to understand why we see this correspondence. And so we developed the Vascular Atlas that is publicly available on GitHub. You will see the link a few times during the presentation. It was based on 42 subjects based on SWY and time of flight at 3 Tesla. And here we computed vascular densities throughout a different region of the brain. And this gave us maps that we could compare to the previous study. Looking at the vascular densities and the glucose metabolism and the fMRI VO or ALF, we saw that the regions that had a high metabolism was also the regions that had a lot of vascular density. Also, there was this paper from Eklund that showed a map of where were localized the false positive in it was based on a meta-analysis of multiple fMRI papers. So basically, the areas that you see here are areas where there's a lot of false positive in fMRI reported in studies. Looking at those maps, and if you put them in the same reference, you will see that those maps are very similar. And for us, it was an evidence that we really need to understand why the common denominator here seems to be vascular density, and so there might be a structural explanation that links all of those modalities. But in order to do this, we need to go further. We need to go deeper than having a vascular sensation coming from SWY and time of flight. Those two acquisitions have different artifacts that we need to overcome, and it's not very informative in terms of more quantitative information, let's say blood flow, susceptibility, and other metrics like this that might be useful to understand why this component seems to appear in a lot of different modalities. And so that was the topic that led to my postdoctoral study. So basically, we wanted to understand how the vasculature impact fMRI measures, and we needed to include more informative data than what was included in our 3T MRI Atlas. So basically, that's going to be the plan of the presentation for today. I'm going to present my 4 different projects that I did during my postdoc. So basically, the first one is going to be the Atlas 2.0, if you want. So here it's based on 70 MRI for an increased resolution, and we're gonna inject some quantitative values based on susceptibility and blood flow. And this atlas was presented during ISMRM last year, and the paper for this atlas is still in progress. When the paper is going to be out, this atlas is again going to be publicly available for alongside my previous atlas. For the next project, we wanted to see even more vessels. So we employ a contrast agent to see more vessels. Here it was a fermoxetol. And here the goal was to try to see if we could find some hidden vasculature that we're not used to see in vivo. Here it was white matter vasculature, and this was presented during 2 ISMRN. And here the paper is in the submission process. After that, I'm going to talk about the Vascular Connectome, which was presented this year during ISMRM. So basically, coming from those fermoxetol data, we were able to build the first vascular connectome linking distal region in the brain. And finally, we want to be able to use this vasculature to try to apply some vascular correction or attenuation of the vascular bias in fMRI map. And to do this, we develop a forward model that we think might be more useful than a trivial masking of the vasculature in those fMRI maps. So first, let's talk about this new atlas. So basically, I said that we needed to have a more informative version of the 3D atlas that we developed previously. However, what I mean by this is that there were some issues that needed to be addressed. So first, we needed a better resolution. So when we developed the atlas, we were limited to a 3T MRI, and we had large voxel size. It was 0.6 per 1.2 millimeters isotropic. It's fine for a multi-subject atlas, and when you do some averaging, it really helps to have large voxels, but if we want precision, we need to have a better resolution. Also, one thing that we often disregard is co-registration of SWY and time of flight. So when you build a vascular atlas like this, and you want to get the arteries from the time of flight and the veins from the SWY, you need to put them in the same reference to make this atlas of the vasculature. But they don't share common structures that much. So that means that when you do co-registration, you rely on putting them on the T1 and then on the MNI space, let's say. So you're not really sure if in the intra-subject space, if those two modalities really align. So we need to find a solution for this. Also, in the time of flight, as I said, you can get the arteries, but you might also get some veins in it because some large veins will still contain some flow. Also, a common problem with time of flight is that some vessels might disappear. What I mean by this is there's a signal attenuation if you follow a vessel. In that is a difficult job for vascular simulation to overpass. So we might see some missing vessels. In the veins from SWY, there's a lot of dephasing effect. That means that there might be some enlarged vessels or some breaks or holes in the SWY that you reconstruct. That means that there will be some disconnection in the whole vasculature. So all of those were problems that we wanted to overcome. And we wanted to add more informative information to the atlas. And for this, we wanted to add some susceptibility measure and of course, increase the resolution, like I said. To add some susceptibility measures, we rely on QSM. So QSM can provide in vivo venous oxygen saturation mapping. So it really, it can be useful for clinical settings or to detect some, not imperfection, but differences between a group of subject and another group of subject. QSM maps are also less susceptible to dephasing artifacts because we can get the direct susceptibility at each point of the vessel, and so we can correct for those dephasing effects, using the QSM map or directly using the QSM map, you get less dephasing artifact. It also provides information for surrounding tissues, of course, and that could be useful for trying to infer the artifacts coming from the vascular structures to the tissues where we measure fMRI. We also wanted to add blood velocity to our atlas. So to this end, we use a quantitative phase contrast acquisition. Blood velocity, you will see in this presentation, it's not really used for now, but it's planned to be included in our models in the last project at some point. It might be useful for modelization. So for example, in van models at the microstructure, they use blood flow in their models, and having this information could be very informative. And more importantly for us, it may help to classify vessels. So like I said, in time of flight, there might be some veins remaining, and as SWY, there might be some holes and breaks. And using flow, we can maybe infer the nature of the vessels that we're looking at more accurately. So basically here, the goal was to use 70 to make the new version of the Atlas, employ QSM and quantitative phase contrast to get susceptibility and flow, and find a method to co-register those modalities more accurately. So in order to do this, we use QSM. So here we use 3 different directions. So for the QSM, it was a GRE acquisition, so a T2 star, with a voxel size of 0.5 millimeters isotropic. But for those who are not really familiar with QSM, you may wonder why use 3 head orientations. It's simply because when you compute the QSM map, there will be some missing data. So that means that at different orientation versus B0 following a conical shape, you will get some holes in your QSM map, meaning that for those areas, we don't have a solution of what was the dephasing. It's like a division by 0. When you try to correct for this, you can either use regularization, so impose a constraint of the neighbors, saying that all the neighbors should have the same kind of dephasing effect. And so you get a blurry image of QSM. You can also use multi-acquisition, like what we did here, so multi-head orientation. So basically, you try to fill the holes, but using different head orientation versus B0. If you use a few directions, then you can get some streaking artifacts. You can get some artifacts also related to the co-registration of those head orientation. So in our case, we use a combination of those 2 approaches. So basically multi-head orientation, but with some regularization in it. So we get a very accurate map that doesn't have a lot of artifacts. From those 3 different head direction, when we compute the susceptibility map, we get something like this, but we can also segment the vasculature from each of those maps. For this, we use the approach that we developed back during my PhD. Also, this approach, as well as the Atlas, is available online at the GitHub link that you see here. It was based on a Frangi computation at multiple scales. It includes a modified vesselness score compared to the classic method. It merged the different scale of the vessels using factor analysis, and then it used some post-processing to get the vascular segmentation, as you can see here. You will see that this approach is used all the time during the presentation. If you want more details, I invite you to see the related paper or the GitHub repository, of course. Using this approach, you get 3 different segmentation. And here, what we found, and that was a little bit surprising, and we were at the same time, it was confirming our hypothesis that there might be breaks and holes into the vasculature at different head orientation. We saw that at the different orientation in this red square and blue square here, that there were some vessels that only appears at different head orientation, and some even disappears at other head orientation. So that means that if you have one single head orientation, for a SWY or a QSM, you will be missing some vessels, and that might impair our analysis. In our case, because we have multiple head orientation, we get a very a more complete map of the veins, the large scale veins here. So combining those different head orientation SWI, you get the map as you see here. And then if you take the QSM map and apply it to the vein segmentation, you get the veins that are colored here by QSM. So you get the susceptibility at each segment of the venous tree. After that, we also, like I mentioned earlier, did a quantitative phase contrast acquisition to get the blood velocity at each segment of the vasculature, mainly the arteries. This acquisition is quite long, but at 7 Tesla, because of the capacity of the 7 Tesla, we can go quicker. And so we included this analysis, but like I said, the flow is going to be included in the atlas, but we won't really use it for now. Now for the time of flight, we use a multi-echo time of flight. So for the time of flight here, we get, for the lowest TE, we get the arteries like what is usually done. So basically, you get a nice arterial map, but for the late, and then on this map, we'll map the quantitative flow obtained from quantitative PC. But for the later TE image coming from this time of flight, we'll also get some veins, as you can see here. However, this vein map is less accurate than the QSM map that we computed just before. But here it will be very useful to map the time of flight on the QSM data because they share a common structure. So basically, we use this multi-echo time of flight to be able to facilitate the registration as well as get a very accurate map of the arteries. So combining the flow with the arteries, we get arterial map like this that include blood flow at each segment. And if you combine the QSMs and the time of flight segmentation, you get this whole brain arterial map, not arterial, vascular map, as you can see here. But here you can map at every segment the blood velocity and the susceptibility. This was done on 18 participants so far. It was, like I said, it was presented last year, and the paper is still in progress. As soon as I'm done, I'm going to share this atlas and also the algorithm to be able to generate them as well. So here, our goal, like I said, for this project was to get a better resolution. I think we achieved that. We added some quantitative measures, and we found a way to facilitate the co-registration by using the multi-echo time of flight and merging it to the combined SWI. We also saw that if you don't use multi-orientation, you might lose some important information in the SWI. And so that led us to think about the importance of having a solution to fill those missing vessels in the brain. That led us to go even deeper and get more vessels and more accurate vessels into the brain. And for this, we wanted to investigate a contrast agent called fermoxetol. So fermoxetol is recently employed for patient that has anemia, iron deficiency. And in our case, it's also a good vessel enhancement contrast agent. But another goal for this project was to investigate this here. So the figure that you see here is coming from a 50 years old histological atlas from Solomon. You can see the vasculature here that is localized in the white matter. And when we saw these figures, we wonder why we could not see those vessels in the regular SWI that we do in vivo. Even if we employ high resolution, we cannot really see those vessels really in those details. Another thing that we notice is that those vessels seems to be very closely related to white matter tracks. And so we kept wondering if there was some common directionality to those tracks here. But before doing this, and then we went back to looking at some papers that did this comparison, and we were surprised to see that there was not officially linking it to myelin or fibers. And to do this comparison, we needed to see those vessels. So that's why we thought that a contrast agent like ferumoxytol might help. So ferumoxytol, basically, it's a myelin-based intravenous iron injection. It has a low but present risk of allergic reaction. It has a long intravascular half-life. So that means that we have a large window to see those beautifully enhanced vessels, but it comes at a cost. So injecting ferumoxytol greatly increase the T2 star decay. And so that translates to an increase in dephasing. That means that vessels that are oriented perpendicular to B0 will be quite enlarged, and vessels, but we can see more vessels. There will also be a lot of noise in the later TE of a T2 star acquisition. And so we need to adjust some parameters when we do the acquisition. But with ferumoxytol, we can also get some high resolution steady state CBV mapping. And it's also useful for having a CBV-based fMRI mapping during tasks. The main advantage here is that you get a really higher percent change. It really depends. In some experiment, it was around 2 to 3 times. In our case, we saw, in this case here, we saw a 2 times increase in terms of voxel activation using ferumoxytol. So it can really help to improve the accuracy of the map that we acquired. But here the goal was really to increase the vascular density. And here we wanted to see if with using ferumoxytol, if it was going to increase the regional density of the vasculature in both the gray matter and also in the white matter. We really wanted to see if we could get the hidden white matter vessels that I just presented earlier. But in order to do this, we need to account for the increased T2 star dephasing. To do this, we employed a multi-echo acquisition. So it had 7 echo T2 star. You can see the echo going through the animation here, and you can see at the post-injection that it gets really noisy really quickly. It's because of this increased T2 star dephasing. So we had a pre-injection session and a post-injection session. Basically, the patient had an injection of 500 milligram of ferumoxytol injected over 20 minutes. And then we waited the 2.5 hours approximately, and we did the post-session acquisition. We had 5 participants that were healthy but had a mild iron deficiency. So they had this clinical treatment of ferumoxytol, and then we basically image the patient before and after their injection. Okay, so let's go back a little bit. So here I just wanted to show the different echo that we acquired post-injection. And as you can see here, if you look at the smallest TE, you early on, you get some dephasing effect, but if you look at the red circle here, you will see that at the later echo, we see more vessels, but of course the dephasing is really, really important. So here we want to exploit this effect to be able to reduce the dephasing effect, but still keep those vessels here. So have a map similar to the low TE, but get those small vessels hidden here. We will employ our vascular segmentation as presented earlier and compute regional density using 2 different atlas, the common free surfer atlas of the gray matter parcellation, but also an atlas of the white fiber bundles to look at the white matter density alongside the commonly known fiber bundles. To exploit this dephasing effect, like I said, we will fit a mono exponential curve at every voxel of this acquisition. And using this curve, we'll get the denoise version of this image that I presented earlier. So by fitting the curve, we get the T at the different echo time. and you get those images here. So we get also the R2 star decay, and we get an N0 image, which is kind of, which here is kind of like a T equals 0 millisecond image. So I mentioned this because basically we are coming from the pre and post, we can compute high resolution CDV maps as well. And normally when you do SWY cementation, you will get the vessel, you will use the longer TE to get the maximized amount of vasculature, even though there's some noise involved, but it's not that important. But in our case, if you do this, you will get too much dephasing. So by fitting the curve and making a TE equals 0 millisecond image here, you get both worlds. You get a denoised image that will include some vessels that you see the later TE here. It's very similar to the low TE, as you can see here, but there are more vessels. So we will use the best images coming from both of the acquisition here to try to compare the cementation. So here's the resulting cementation pre versus post injection. Here you can see the whole brain vasculature, but if you look at different areas, here's the gray matter vessels. So basically we took the white matter surface and show the vessels that are above this surface. And then if we look at the white matter vessels, you can see that before the injection, the vessels that we got were kind of disconnected. It was more related to noise. So normally when you get those vessels like this, you discard them because they don't seem to be structurally to show was that basically we fit a mono exponential curve at each point of the image here. There's a neighbor's constraint, and that allows us to have a denoised version of the multi-echo image, as you can see here. But here, what we will do for the comparison is use the best image of this multi-echo reconstruction images here. The best images are normally without injection, you take the longer TE images because they contain more vessels.
Mike, very nice images. I think it's great that you are adding the quantitative flow to measure the arterial flow velocity and quantitative QSM to add essentially sort of the venous occlusion information. But I was wondering, how do you plan to account for the partial volume effect? Because for small arteries and small veins, both index will sort of suffer from partial volume effect.
When you mean partial volume effect, you mean in the cementation or in the flow and
in the flow value you are giving? For instance, taking quantitative flow, for example, when you look at a small vessel, when there's a partial volume between vessel and tissue spins in the same voxel, the estimated flow velocity will be underestimated because the phase angle will be smaller than it actually is. And same thing can be said for QSM. When you measure susceptibility, you are sort of indicating those are related to the deoxyhemoglobin amount and essentially oxygenation. But a small vein, a partial volume vein would actually give you you can say a higher YV than it really is, or lower OEF than it really is. So these are the partial volume effects I was referring to.
Okay, but it's in fact, that's a very good question. So for now, in terms of flow, we didn't do any partial volume correction. So the way we did it is we get those flow information and we take a neighborhood average at every segment of the voxel. But as you said, larger voxels and smaller, larger vessels and smaller vessels don't have the same partial volume effect. It might be interesting to include some partial volume correction to it. I think it's a good suggestion. We need to investigate this. For the QSM, we think that in the resolution of the QSM, this partial volume effect is less important than in the flow acquisition. Again, here it's going to be presented later, but we simply map on the vasculature in the surrounding QSM values on the vessels. Because we get the smaller vessels also in the QSM map, we think that this portion volume effect is reduced. Basically, it's less important.
Thank you.
We compare the vascular density in the different gray matter regions. And after looking at the post-injection images and comparing to,
sorry.
In comparing to the pre-injection images, we saw that the same region seems to correspond in terms of vascular density compared to the other regions. It's just that there is an increase of vascular density of between 3 to 4 times more vessels using the femoxetol injection. You can skip. And then looking at the white matter, we saw that, of course, in the post-injection image, we can see that some fiber bundles seems to be more vascularized than others. And a colleague of mine did a comparison of the bold fluctuation into in every white matter bundles. And we saw that the fiber bundles that had the highest bold fluctuation in them were also the one that had the highest vascular density, which is in concordance with what we presented earlier. We also, here I wanted to show the resulting cementation, but alongside the whole brain white matter tracks. You will see the white matter tracks appearing soon. So basically, we wanted to show how those white matter tracks seems to follow the vasculature that we obtain. Of course, we're comparing probabilistic tracks with segmentation. So it's two complex data that we're trying to compare that are not supposed to be compared like this. But looking and seeing this evidence for us, it gives us confidence that we're going in the right direction. We can also, if we skip to the next one. We can also see if we isolate some white matter bundles, you can see that the vessel seems to be aligned with the white matter bundles as well. Looking at each and every one of those bundles, we saw that there's a qualitative coarse correspondence between the cementation, but it's not a perfect match, of course. We didn't expect a perfect match. It's not the same the same anatomy that we're looking at, but it seems to be related to the what we were expected to see. If you go to the next slide, yeah, okay. So here we did the comparison in every bundles, and I'm trying to skip. And so I think we show that we achieve our goal, which was to increase the vascular density of the visible vasculature using femoxetol. We uncovered white matter vessels. We were quite happy to see this. We took advantage of the multi-echo images and used the lowest TE image, and we found a qualitative match of white matter vessels and white matter tracks. But now, how can we use this toward applying this beautiful vascular cementation to understanding more how it relates to Fmri? And that was basically our next step. So we saw some studies from, for example, Molly Bright, looking at the vascular component of the resting state network. And for us, it was very inspiring. We wanted to basically do an approach that is similar, but based on the vascular connectivity of the distal region of the resting state network. So in order to do this, we needed to build a way to follow those segmented vessels and build a vascular connectome. And that was the goal of the third project here. So build the first vascular connectome and then be able to use this connectome to compare it to a resting state connectivity connectome. So Like we mentioned earlier, there seems to be a link with vasculature and tractography. We need to find a way to put those two modalities in the same referential to be able to compare them. And also, we trying to advance, okay. And also we want to understand how the bold fMRI that we saw in the white matter seem to follow those vascular tracks that we can, those vascular vessels that we see in the white matter. So you may be familiar with John Gore's recent analysis of the white matter bold. He was building seed-based bold connectivity in the white matter and saw some correspondence between bold-based tensors that we can reconstruct in the white matter and DMRI tensors. So inspired by this, we wanted to do something similar and go towards DMRI approaches to be able to do this analysis here. So as I mentioned, previous studies compared white matter connectivity with functional connectivity. In our case, we want to add the vascular connectome, but it's hard to do because, as you can see at the bottom left, the vessels, we are at the limit of the resolution that we can achieve at the scanner using this spherical. There might be some broken edges, so we need to find a technique that will overcome those broken edges and really connect those distal regions here. So here, what we want to do is, based on this concordance between the vessels and the white matter tracks, we wanted to use pre-established method coming from the diffusion MRI to be able to use the same approach to reconstruct tracks, but here based on the vascular cementation. So in order to do this, we need to basically trick the DMRI the DMRI track reconstruction algorithm so that it thinks that we're feeding it basically a DMRI file. In order to do this, we need to modelize the different direction of the vessels, but it's not a simple task. So intuitively, we could use a spatial tensor to represent the direction at every point of the vessel. We can use this intuitively because basically it's based on because the cementation is based on a Ferengi analysis. So it's based on the Hessian or second derivative of the images, but at multiple scales. So large vessels have a certain scale, and smaller vessels have a lower scale. So having a multi-scale spatial tensor representation is not strong enough because it will be hard to modelize the different direction that the vessels can take, and you will end up with a broken connection at every point. So we need to use what was employed in diffusion MRI and modelize the direction using basically a ODF. You can advance. And basically use an ODF, which is a multi-direction representation of a local multi-direction representation of where the vessel can go. But to compute this, it's not simple. You cannot use a cardinal derivative. And so you need to do basically what we see at the top right. It's line derivative. We kind of modelize the line derivative following a sphere. It's based on what we see in multi-field sampling. Here we use different size of those sphere, if you want, to capture the multi-size of the vessel. So we inject the multi-scale the multi-scale anatomy of the vessel in the method using this different line derivative size, and we can apply this line derivative at as many directions as we want, as many level of vessel size as we want. In our case here, I present 60 directions spread on 4 different level size. So basically employed filters of 5x5, 7x7, 9x9, etc. Here we can see the ODF that got reconstructed using this method. they are ODF simply localized on the vascular cementation here because we reconstructed the ODF at this localization. And then if you launch any tracking algorithm from this here we will launch probabilistic tracking. You can skip to the next one. And here we modify a little bit the tracks so that it captures the anatomy of the vessels. It means that we need to have a higher step size compared to what's used in classic diffusion MRI, because we need to overcome those breaks in the cementation that I talked about earlier. We'll also use way longer tracks that we want to keep, simply because the vascular anatomy is not going straight into a region. So we need to capture this sinuous anatomy of the vessel. And here I show the vascular tracks from it stopped at 20,000 tracks. You can go to the next one. Looking at the tracks that we obtained, we were wondering if it was following the anatomy correctly. And so we put them on top of the vascular cementation that we had. And here you can see, it's going to zoom, that the tracks that we reconstruct really follow closely the anatomy. And if you go to the next slide, based on this whole brain construction, we can build a vascular connectome. So basically isolating the tracks that connect to distal regions. We can also do this algorithm by launching the seed from a region here. And you will also get the same kind of vascular connectome. So here we're able to provide this first connectome here, and you can skip. And it will be, we will be able to make a comparison with the MRI connectome or Fmri connectome. And we do hope that it will provide some explanation and some link to what Molly Bright presented in another study, so that maybe some more vascularized region have some strong connection, and so maybe it's one of the explanation of why those distal regions seems to be so connected. So it might help to for understanding of resting state connectivity. So this is still this need a lot of validation. It's the first draft of building a vascular connectome, but we think we were successful in making this step. You can skip. Now, based on this, we think that this might provide an explanation of the origin of the bold signal connectivity that we saw in the white matter, but also an explanation on the large scale of bold connectivity. But now you can skip. For the last project, we wanted to basically use all those fancy vascular cementation that we obtained and find a way to modelize what's the effect of the vessels going to be on the Fmri map. And we need to find a way to take those vessels and basically transform them to a way that we can see the dephasing effect that will cause in the surrounding tissue, and then correct Fmri map based on those cementation. Because we know that the vascular contribution of the vasculature in bold is not straightforward. I presented at the first slide of my presentation, and it's been proved. There's been some evidence in the recent literature going towards this. Also, we saw that there's an orientation effect of bold coming from a work from my colleague. So basically, bold will vary based on the orientation versus D0. And in classic methods to remove the vessel contribution in Fmri map, we either mask the vessel out simply or use decomposition to try to understand how if there's some vascular component in the Fmri map and try to remove it. And some others use a distance from the large vessels to try to correct or understand the effect of the vessels on Fmri map. But we think that based on what I presented earlier, we need to go beyond that. And so we know that the vessel size and orientation versus B0 is important to be taken into account. And in those previous studies, it was not really taken into account. So we know that the signal fMRI coming surrounding vessels can vary from up to 50% based on if it's close to a vessel that is perpendicular to B0. And so we need to build a model that will take this into account. You can skip. So our goal was to basically build what we call a forward model based on the local magnetic perturbation surrounding the vessels. Basically, this work is based on the microvascular study like VAN models that use blood susceptibility, flow, and localization of the vessel size to try to modelize a bold response. But now we want to take these microvascular models and make it to the macrovascular size scale. However, here, you can go back, sorry. However, here, we will not use the blood flow yet. So we wanted to concentrate ourselves with the susceptibility at each point. But at some point in the future, we will try to add the blood flow to this model. So basically here, we will use from the atlas that we had earlier, the QSM, estimate from this a vascular field offset, and then compare it to task-based fMRI acquisition. You can skip. So skip again. Basically, we had our vascular segmentation, we had our susceptibility map. We can then map the QSM on the veins at every point, and then we can build we can use the finite perturber method to basically map for every point of the vascular tree what's the dipole effect at this localization. It's basically a convolution with the dipole effect coming from a cylinder shape. And then using the susceptibility orientation and size, you get extravascular field offset map. And then if we vary the oxygenated and deoxygenated concentration in the model, you can, let's say you get you can simulate an active state of plus 10% of SO2, and then you get a baseline map and an active map. If you take the difference between the two of them, then you get an estimation of the field offset based on an activation of 10% of an estimation of 10% of both activation. So using this field map, we did this on all our atlas subjects, and we get here for a single subject the field map on a single slice on the left and the field map on the right projected on the gray matter surface alongside the vessels here. If you look at the vessels that are perpendicular to B0, you can see that there's a large effect, large field offset surrounding those vessels. And if you look at the smaller vessels perpendicular to B0, this effect is smaller, of course. Then if you look at the vessels that are parallel to B0, you will see that there's low or absent amount of field offset coming from those vessels. So it's to really follow what we expected the model to do. We also computed this, like I said, in all our subjects. We computed the mean of every subject. This gives you this field offset map here. And what's surprising here is that it seems to be very consistent across subject. And for us, it's a good news because we might be able to use this atlas as a way to correct our fMRI map. So we don't need to have a single subject vascular segmentation to be able to do this approach. We might be able to use an atlas to do this. You can skip. So here an example of a potential fMRI application. So if you have the veins here, you can obtain the field map that we estimated using the previous method. And then you get a fMRI activation map coming from a visual task-based fMRI. So here you can see the percentage of activated area from this visual task, for example. If you look at the field map and you remove the vessel, you get the field map as you see here. And then if you put it at the same resolution as the fMRI, you get this map here. And if we mask the region of the field map related to the activation of the fMRI, you get this field map here. And then if we take a closer look at this field map, you will see that, you can skip. You will see that in the classic approach, we will simply mask out the vessels located at this area. But if you look at the different region here, it might apply correction where we don't really need correction, and it might don't apply correction at places where there should be more correction. But if we divide our image by the field map, you will get what you see on the right here. And what's comforting us is that if you skip again, is that in some areas, let's say here around the brainstem, you will see that the field map really capture the contribution of the vessels that we don't want to see in the fMRI map, and it's really tried to remove this contribution here. But if you simply use the vascular, the vein mask, it will not remove those areas here. So we think that we are approaching a solution that might be better than masking the vessels, but of course, this is a proposition that needs further validation. It doesn't take into account blood flow, so we need to improve this model. But we think it's a good step in the right direction. You can skip. So basically, in the summary of all what I presented in 3 parts, let's say, we build a new 2.0 version of our atlas using a 70 MRI acquisition based on 18 subjects. It includes blood flow and susceptibility. We think that this map is more accurate than what we had before. We think that we improve the quality of the QSM and time of flight mapping using a clever approach of multi-echo time of flight. And we're happy to provide this atlas as soon as the paper is published. You can skip. We also computed a way to apply this vascular map to compute a vascular field offset, which I just presented. We think it's accurately improved it's a more accurate way to correct a fMRI map better than masking the vessels. And what's very important is that it's very consistent between subjects. So we might be able to use this 70 MRI atlas to do this kind of correction. And finally, I presented this new version of this now in vivo version of this histological study where we tried to see the white matter vessels, but now on top of it, we put the white matter tracks. We saw a correspondence between the tracks. Using this, we're able to connect distal region in the brain using a vascular connectome. And we're happy to provide the first vascular connectome of the human brain. And finally, thank you for inviting me, and sorry about all the technical problems. Sometimes things like this happen, I guess. And thank you for staying all the time and looking at us trying to struggle with those. And of course, I'm happy to answer to all your questions either here or by email. Very happy to be able to show this work. And again, thank you for inviting me.
Well, thanks so much, Mike. First off, thank you to you and everyone for staying patient during our technical difficulties. And again, I would